You ever wonder how your favorite song sounds so incredibly crisp? Or how a medical scan can be so sharp and clear? Well, a lot of the time, it all comes down to some really clever digital filtering. So today, let's dive into that whole process. It's a journey, really, that takes us from this perfect but totally impossible idea to a practical tool that literally shapes our world.
At its core, the problem is pretty simple to grasp. How do you get rid of all the unwanted digital noise and just keep the clean signal you actually want? You can think of it like needing a digital sieve, but how on earth do you design the perfect one? Well, you start with a dream, a perfect, theoretical filter that acts just like a brick wall. It lets everything you want pass through perfectly, and it slams the door shut on everything you don't, instantly. It's flawless, in theory. But as we're about to find out, reality has some very different plans. All right, step one, you got to draw the blueprint. So if we look at this in the world of frequencies, our perfect low-pass filter looks like a simple, clean rectangle. It's got a gain of 100%, or 1 in what we call the passband. That's all the good stuff, the frequencies we want to keep. And for everything else, a gain of absolute 0. Simple, clean, and perfectly defined on paper.
So a blueprint is great, but you can't build anything with just a picture. You need instructions, and that means we have to translate our perfect idea from that abstract frequency domain into the time domain, which is, where real systems actually live and breathe.
So how do we do that? How do we make that translation? For step 2, we use this really powerful mathematical tool called the Inverse Discrete Time Fourier Transform, or IDTFT for short. Just think of it as our universal translator. It takes that frequency blueprint, the what we want to filter, and it converts it into a super precise step-by-step set of instructions based in time, the how we're actually going to build this thing. And this right here is that translator in action. This integral takes our perfect brick wall idea, you solve it, and what it spits out is a whole series of numbers. We call them coefficients. And these coefficients, this h of n, these are the exact moment-by-moment instructions for building our perfect filter. Okay, so we've done the math. We have the perfect instructions. We're ready to build, right? Well, not quite. This is the moment where that perfect theory crashes head-on into reality. Turns out there's a huge fundamental flaw in our perfect plan. I mean, we have it. We have the recipe for the perfect digital sieve. Every single coefficient is calculated with absolute mathematical precision. It should work.
But here's the billion-dollar question. Can any real-world computer or processor actually follow these instructions? And the answer, maybe surprisingly, is a hard no.
And here is exactly why it's impossible. See, our perfect recipe makes two demands that no system in the real world can possibly meet. First, the instruction list is literally infinitely long. You'd need a computer with infinite memory and processing power. Good luck with that. Second, it's something we call non-causal. And what that means is, to figure out what to do right now, it needs to know what's going to happen in the future. It's basically science fiction. So, if perfect is impossible, what do? We just give up? Of course not. We do what engineers do best. We make a smart, practical compromise that turns the impossible into something that's actually possible. The solution is actually beautiful in its simplicity, even if it is a little blunt. It's called truncation. We take that infinitely long list of instructions and we chop it off. We decide on a length that's manageable, and we throw away everything else. This is what's known as the without windowing method. It's an abrupt compromise, but it works. So how long is manageable? Well, the length of our filter, which we call L, is determined by its order, N. The higher the order, the longer and more complex the filter gets, but the closer it gets to that perfect ideal we were aiming for in the first place. It's a trade-off. And now we're on the home stretch. We have a couple of final but really critical steps to bring this all together. Step 3 is to use something called the Z-transform on our new finite set of instructions. This gives us the final practical recipe, which is called the transfer function. Think of that as our master blueprint. Then, for step 4, we use that blueprint to design the actual hardware or software structure, the specific layout of delay elements, multipliers, and adders that will do the real work. And this transfer function, h of z, this is the whole shebang. It's the ultimate goal of the entire design process. It's the complete, buildable recipe for our real-world filter, and it came directly from that compromised but totally practical set of instructions we made. Okay, I know that was a whole lot of theory, but how does all this abstract math actually get used to solve real problems? Let's make it concrete with a quick example.
Right. An engineer doesn't start with radians and abstract ideas. They start with real-world specs, just like these. They need a filter that cuts off everything above 500 Hz for a system that's sampling at 2000 Hz. Their very first job is to take these real-world values and normalize them into radians. That's the language our whole design process speaks. And from there, they can follow the exact steps we just walked through to build the filter they need.
And this is where you really see just how vital this all is. We're talking about the audio filters that make your music sound so clean, the image processing inside an MRI scan, the wireless signals bringing you Wi-Fi and 5G. This exact design process is the hidden engine behind so much of our modern technology.
At the end of the day, that's what this is all about. It perfectly sums up what engineering is. Taking a beautiful, flawless theory that just can't exist in the real world, and then making the smart compromises needed to create something real, something useful, and something powerful. So the next time you listen to a crystal clear song or see a super sharp digital photo, you'll know the incredible journey it took, from an impossible idea to a practical reality. It really makes you wonder, right? What other invisible engineering, what other bits of math are quietly shaping the world all around us?